Hello, everybody. I hope you're all doing fantastically and you're ready for question number 5 on our Euclid paper. Triangle ABC has vertices at 0, 5, 3, 0, and 8, 3. I'm sensing a right angle triangle here. And we can even draw a picture. So what was it? 0, 5, 3, 0, I think. Oh, and then C, no, C's not on there. Oh, that's a shame. So C is at 8, 3, so I guess that would be somewhere about here. Okay, that seems reasonable, I guess, as a picture. We want to determine the measure of angle ACB. So I want to know this angle out here. I'm going to, with my powers of deduction, assume it's 60 degrees and that this happens to be 90. But I don't know that for a fact, actually. Okay. What could we do here? We want that angle. Trying to think the best approach, the one that takes the least time. Although sometimes you can worry what the best approach is too long, and then you're wasting your own time. I suppose. Well, I really think this is probably a right angle. So on a hunch, on a math contest, having done at least 5 math contests in my life, I'm gonna guess that that's a right angle. It really looks like it, but maybe that's just my picture. If it's not, we'll try something else, but on a hunch. So the slope of this line, we're at 8, 3, 3, 0, and 0, 5. So on a hunch, the slope of this should be 8 minus 3 over 3 minus 0. So that should be 5 over 3. And the slope of this line is going to be... Oh, sorry. I got my x's and my y's messed up. 3 minus 0 over 8 minus 3, so this should be 3 over 5. 5 minus 0 over 0 minus 3, oh, look at that, it's negative 5/3. So these two slopes are perpendicular because one is the negative reciprocal of the other. Okay, now how exactly does that help us? Great, it's a right angle triangle, but what exactly are you going to do with that right angle triangle? Well, I also suspect this is probably a 60-degree angle. Now, how could I show that? How could I prove that? Okay. And I really do genuinely just suspect this is 60 degrees. I might be right, I might be wrong. What could we do? Well, we could try some trigonometry. Or I'll tell you what, if the length here is, let's call it L, if this length is 2L, then that would definitely have to be a right angle triangle, and this length here would be root 3L. So is there a way to show that? Well, whatever this length is, it's the hypotenuse of this triangle here, which goes over by 5 and up by 3. Okay. So, I don't think it's going to work. I was hoping we could go over by 5 and up by 3 and over by 5 and up by 3 again. Because then if this is L, then I've got 2 L's. But it looks like that's not the case, because you'd have to go over by 10, and we're only at 8. Not over at 10. It's not, C isn't at 10.3. Okay. So I was right to gamble for the 90 degrees. I wasn't so right to gamble for the 60 degrees. What can we do? Well, I suppose we could probably figure out this length, and then opposite over adjacent. So the tan of this angle that I want is opposite over adjacent. Grab my calculator. That doesn't hurt. Okay. So how do I figure out this opposite? Well, notice in this red triangle that it's the hypotenuse, and we've got 3 and we've got 5. So O should be the square root of 5 squared plus 3 squared, which is 25 plus 9, that's 34, so square root of 34. Now, how about A? Well, if we take a look at this green triangle that we drew not a moment ago, you go over by 5, up by 3, and oh, look at that. It's going to be 5 squared, 3 squared, root 34. So it's going to be, so the tangent of this thing is 1. This is an isosceles right angle triangle, and so I don't even need to grab my calculator and do any SOHCAHTOA stuff. Automatically, these have to be 45s. So the angle we're looking for must be 45 degrees. There we go. All right, so it's nice to gamble. That's why I like to draw my pictures before doing any of the actual calculations. I get a real sense of what's going on, and I was right to guess that it was a right angle triangle. I suppose if I'd drawn in the green triangle and red triangles earlier, I could have seen that, oh, this angle must be the same as this angle, and this angle must both, so we get 90, so there's an easy way to see a 90 there, but that's okay. That was only A part. We've got B part left to go here. And this is the one we actually have to show our work for. In the diagram, PQRX is an isosceles trapezoid. Oh, kind of like the isosceles triangle we saw earlier. So that means we get these two sides here. The non-parallel sides are both the same length. We've got PQ is 7, and both of these are 8, and then the bottom here, the base is 15, and we want to know the length of diagonal PR. 7 and 8. I feel like 7, 8, and 5 make a triangle with 120 degrees or something like that. It's irrelevant, it's just something that's popping into my head right now. Okay, well, let's draw this picture and see what we can see. Actually, you know what? Let's draw a slightly bigger trapezoid. Okay, so I've got 8 here, I've got 8 here, 7 here, 15 here. Now we want to get PR. I'm willing to bet that we probably need to extend out here to point T. So actually we'll leave it and say that. Because we do have to write up our solution after all. So extend PQ to T above R so that PTR is right angled. Okay. Then TR is H is the height of the trapezoid. Okay. And so if I knew what TR is, which we called 8 or H. So if I knew what that was, and I knew what QT was, so let's give that a name. Let's let QT be G. Then PR is the hypotenuse of QTR, which has legs H and 7 plus G. Okay, how am I going to find out what G is? Okay. Well, we can drop perpendiculars. I'm only doing it over here with P and U for symmetry, but let's see, we get Q here, Q to V. So we'll have to write that down. We'll say drop P to U and Q to V on SR. So PU and QV are perpendicular to SR. Okay, so we dropped some more heights. PU is QV is TR. These are all what we're calling H. Okay. And we can see that QT is the same as VR. Is the same as US. Now, why this one? Because triangles PUS and QVR are congruent because they both have 90 degrees, and we've got the same hypotenuse, 8, and the same height of H, whatever it is. So you can use Pythagorean theorem to get this other side here. So we got G's here, H's there. Okay. Now, we can see PQVU is a rectangle. This is actually a fairly common thing to do with trapezoids. So I see that VU is also 7. So SR is 7 plus 2 copies of G, but we were told that SR is 15. So I can work out that G must be 4. Okay. So we get 4 here, and 4 here, and 4 here. So now I know that PT is 11. I don't know the height yet, but I can use the fact that I've got this hypotenuse 8 to work out H. So then by Pythagoras, H squared is 8 squared minus 4 squared, which is 64 minus 16, which is 48. Now, if you wanted to, you could square root that. You'll get H is 4 root 3, but I'm thinking ahead for a moment. It's a good idea to do that sometimes. What am I about to use H for? So PR is the hypotenuse of triangle PTR. So PR squared is what? H squared plus 7 plus G squared. And we know what H squared is. It's 48. We don't actually care what H is. We don't use that anywhere in the question. But H squared, yeah, we use that. And then we'll get 11 squared. So that'll be 48 plus 121. And that'll be 169. And so PR, this length that we wanted, this diagonal, must be 13. Fantastic. And there we go. We've shown all our work. Nice, clearly labeled diagram, naming things. We even, state the. You could, I suppose, say, better explain why these are congruent. I think it's a little clear. But that's about the only thing I would really touch up. Everything else is nice and clear. Calculations are being done. It's very obvious in reference to the picture what's going on. So there we go. That does it for question number 5. On we march to question number 6. We are officially over the halfway point in terms of the question numbers for our Euclid. But as we'll see, the questions should get a little more difficult as we go on. I'll see you for 6 next time.